Good morning and afternoon, all. Charlie Vartanian from the Pacific Northwest National Lab, here to open and introduce today's energy storage webinar, being brought to you by the PNNL Grid Storage Launchpad. This is one in a series of informational webinars being given, and today we have a very special focus and topic and set of panelists that are going to talk about power electronics as an energy storage enabler. Batteries, by nature, DC devices, and to get them connected to exchange energy and power with the grid, they need to go through a device that converts the DC to AC, and that's primarily today inverters. So among our panelists are on that, an inverter-based resource expert working at the North American Electric Reliability Corporation. We have Amir Mohammedur from SoCal Edison, a senior engineer who's a specialist in system studies, which includes the modeling of inverter-based resources, including energy storage systems. We have Pat Hayes, a veteran of ABB's North American Energy Storage Inverter and Energy Storage Systems businesses. And I think it's a real strong market indicator that now he's a director-level product lead in ABB's new high-power charging product line. I'll be touching on that. And we're really honored to have today's moderator is Dr. Leo Casey, currently of X, the business development incubator portion of the Alphabet companies, former CTO of SatCon. At one brief moment, they had the largest market share of PV inverters in the world. I think that's correct, Leo. But more importantly, he has been driving the power electronics for grid connected devices, whole practice, technology, its application forward for a long time. So he's going to be pushing our panelists to bring forward their key thoughts and ideas for this audience that has a wide-ranging composition usually, regulators, battery scientists, utility folks. So panelists, do keep that in mind while you're deep experts in power electronics. We're going to be addressing a general audience today. Slide 4, please. A couple thoughts to share before we hand it over to Amir to kick off the panel. To those working within this area, this is not new, but it's not just batteries that are connected by inverters. It includes PV, which, the prime mover, the basic energy and power resources DC. It goes through a DC to AC converter. More and more, even rotating machines, microturbines, for example. But the point here is power electronics are ubiquitous. So the nature of how they operate will make a massive difference on the performance, the reliability, and a key issue is, will it set an environment to hit higher level policy goals like increased renewable resource penetration while maintaining reliability and also keeping costs in check. I'm a personal advocate that we could hit very high renewable penetration while maintaining grid reliability and holding average system costs. Next slide, please. So as inverter-based resources, including energy storage, are more present, a higher proportion of the resource portfolio across all systems. They do have attributes, and it's a strong term, but there is a penetration point at which they will dominate the dynamics, i.e. what is the voltage and frequency stability of the grid? Can we hold nominal voltages, nominal frequencies? I'd say that's more of the protective, and that's been a perspective out there regarding inverter-based resources, as a lot of the early standards were, I'll call it protective, do no harm to the grid. But there's new perspectives flipping that around. Well, they have such, let's say, high resolution, fast control response capabilities that we could flip that from mitigating risk to leveraging their capabilities to increase renewable penetration. Again, while maintaining or even increasing reliability and power quality. But whether it's technology, economics and markets, regulatory, there are going to have to be changes to fully enable and access and utilize those capabilities. So we have one of the largest utilities in the US that is at definitely the forefront of inverter-based resource adoption, SoCal Edison. We have the Electric Reliability Organization for North America, NERC. Here, they set the rule of the road. The backstop reliability criteria are set by them, and they're looking hard at inverter-based resources. And then we have someone that has to make a business case, in this case for high-power EV charging. With that, we'll go right into presentations. Kicking it off with SoCal Edison and Amir.
Thank you for the introduction, Charlie. Hello, everyone. My name is Amir Mohammed Nur. I'm a senior engineer at Southern California Edison, and I work in the transmission planning group. And I'll be talking about some of the things that SCE has done related to battery energy storage as an enabler of this technology, including a joint study that we did with PNNL that looked at energy storage as a potential solution to the declining system inertia that our grid faces as the penetration of inverter-based resource increases, displacing traditional synchronous generators. Next slide. A quick background about SCE service territory. SCE is one of the largest investor-owned utility in the US, providing power to over 15 million people across central, coastal, and Southern California. And our territory covers over 50,000 square miles, which consists of a vast infrastructure in order to reliably deliver the power to our customers. And currently we have approximately 2,275 megawatts of large scale battery storage installed on our transmission system. Next slide. California is committed to addressing climate change and has set goals for the state to achieve carbon neutrality by 2045. And SCE published a white paper in 2019 that gave our perspective on what it would take to transform the industry towards a clean energy future and achieve the decarbonization goals. The white paper identified 5 key sectors that would need to be decarbonized. This included the electric sector, where 100% of the load would be served by carbon-free resources. Electrifying buildings so that 70% of homes and business buildings will use electric space and water heating. Electrifying the transportation sector so that 75% of all vehicles will be electric. For those sectors that have difficult to electrify, 43% will need to switch to low carbon fuel alternatives. And the remaining carbon in the atmosphere will have to be offset through natural process, such as planting trees. In order to achieve this transformation and meet the expected load demand, it was expected that California would need to integrate gigawatts of renewable generation. And this is both on the transmission and the distribution grid. And in order to have sufficient resource capacity during peak conditions when the sun is not shining and wind is not blowing, we've identified the need for 30 gigawatts of utility scale and 10 gigawatts of distribution scale energy storage. Next slide. This is one example of how energy storage is being used in California to support the reliable operation of the grid. Last year in early September, California was hit with a severe heat wave where CalISO grid experienced a new peak load record. And CalISO was able to avoid load shedding to be able to balance the load and generation demand, mainly due to 3,500 megawatts of battery energy storage that was procured since 2020. And you can see from the diagram on the right, during the peak hours where solar resources were starting to taper off, energy storage was able to kick in and supply the energy needed to meet the load demand. Next slide. Now, Reduction of system inertia is a growing concern for the industry as we start to integrate more inverter-based resource technology and retire traditional synchronous machines. So as part of our Pathway 2045 assessment, we performed a joint study with PNNL that looked at really low inertia scenarios and investigated whether battery energy storage with fast frequency response, or FFR, could be a potential solution. And the study showed by including 1,000 megawatts of storage in SCE system and 260 megawatts in San Diego, with fast frequency response capability, you can potentially eliminate triggering under frequency load shedding and significantly improve the minimum frequency observed during large disturbances. If you look at plot A on the top right, this shows the system performance with different droop values, also with and without FFR capability. And you can see in blue that with a smaller droop gain and no FFR capability, the system frequency can potentially reach UFLS thresholds. On the other hand, in purple, it shows with a larger droop gain and FFR capability, the minimum frequency can be significantly improved. And the plot below shows a response of the 1,000 megawatt energy storage resource that was modeled in the study, and how a 1% droop setting without FFR can output a large amount of power, but with a significant delay of 15 seconds, compared to when FFR was enabled, which was able to output the same amount of power, but in about 2 seconds, which was fast enough to contribute to the initial part of the frequency drop and arresting the frequency nadir. Next slide. So as we transition, these are some of the challenges that we face trying to integrate energy storage. One of the big ones is abnormal performance from energy storage during system disturbance. And this is similar to what we've seen with PV resources in recent grid disturbances in California. It's extremely important that these resources remain online during the disturbance and contribute to system recovery and reliability. We're starting to see limitations with our traditional positive sequence tools in order to accurately model, simulate, and study the impacts of inverter-based technology. Obviously, grid stability is a big concern when you think about a system with 100% renewables. We started thinking, are these resources going to perform as expected with minimal synchronous machines on the system? Can energy storage contribute to system strength and provide some of the essential services that the grid needs to operate reliability? And having adequate land space may also pose some challenges in trying to get large-scale energy storage near our load pockets in the metropolitan areas. Another is, since electrification of the residential sector will play an important role in achieving California's goals, it's going to be important to make sure that energy storage will be affordable across all customer classes. And lastly, 100% electrification can lead to potential supply chain risk for energy storage technologies as the demand for certain minerals and metals increases.
Leo, if you don't mind coming on with your mic and your camera, we're in 5 minutes of Q&A.
Can you hear me, Charlie?
Yes.
Okay. So Southern California Edison have been pioneers in storage going back a long time. When I met Charlie about 25 years ago, there were really only 2 grid-connected batteries in North America. One being the famous NICAD system that SAF put in Alaska, and of course the other one was the Chino Hills. Amir, you're one of the few utilities that really have, developed through your earlier white papers a plan to go forward. What do you see other investor-owned utilities doing in the country? And then what do you see happening in the world of sort of costs and reliability?
So I know there's a lot we can learn from like Australia and Hawaii Electric, and we're trying to leverage as much information in the industry. One of the biggest things that's been helping us too is participation in the NERC IRPTF task force that's highlighted a lot of really good recommendations that we've adopted, to ensure that a lot of these resources are operating as expected. And it's a big concern, as we're seeing some of these disturbance issues result in abnormal performance from these resources. It becomes a big concern for us, when you think about 100% penetration. So one of the things that we have done is adopted some of the recommendations from NERC, and this is prior to the IEEE 2800 standard being developed. That's developed minimum capability requirements for inverter-based resources. But we've adopted a lot of new performance requirements based on the recommendations from NERC to ensure reliable operation with inverter-based resources.
Yeah, we we have the NERC presentation coming up. Charlie and I were involved in with NERC the investigation of the Southern California instabilities and problems about 5 years ago. This is the Canyon and the Blue Cut fire-related instabilities. It's interesting that if you actually look closely at the NERC reports, it's very seldom anything to do with sort of grid forming, grid following instabilities. It's all about things going into the field where we don't understand when they will trip, and losing a large fraction of the inverter connected renewables, very suddenly, that then cause major system outages, and particularly the ERCOT case comes up. What do you see happening in the area of costs?
So cost is, a big thing for us. Affordability. Our main goal is to keep the grid reliable and obviously affordable, and making sure that some of this technology is easier to access and have some type of financial incentives to offset costs, like some of the things that are maybe like providing rebates and things of that nature.
So my magic number is $1,000 a kilowatt hour, which comes out of both Bloomberg and sort of companion reports, and I would trace that back to someone like Richard Baxter. Do you see anything substantially below that in the world of lithiums?
I'm not sure if I have a good answer for that question.
Okay. I just want to briefly acknowledge that one of the incredible pioneers of grid-connected storage is actually in the audience today, and that's Hawk, who developed at Detroit Edison large flow batteries sitting on the back of trucks as non-wire alternatives 30 years ago. So, Hawk, it's good to see your name here. In the world of PV, the inverter is interesting because it can do a lot of things other than provide real power. It can provide obviously reactive power, and then all sorts of variation of sort of reserve power in terms of harmonic cancellation and voltage spike suppression and the like. But the inverter is going to run out, a fraction of the life of the plant. Maybe it gets to 10 years. In the world of storage, it's a little bit different, right? The inverter is really not the least reliable part of the system. What's your experience there?
As far as, can you repeat that, the reliability versus?
Yeah, well, so it's either needing to sort of wholesale swap out the inverters because they've aged, because there's way too many plastic parts in modern power electronics, and or just it's the thing that fails. It's the thing that cannot really tolerate an overvoltage or an overcurrent. So
if we're speaking strictly from, because I can only talk from a transmission planning perspective, and when you talk about performance, the main thing that we focus on is, making sure that these resources have like write-through capability. You mentioned voltage support, and what our study with PNNL showed is also, having fast frequency response capability. And there's a whole other, when you think of future 100% renewable resources, like ability to contribute to system strength and, can operate in a weak grid condition. Things like those also, play a big factor in energy storage.
Okay, my final question, and I think it's a really important issue that you raised, is that, you know, the Australians maybe 6 or 7 years ago threw up their hands and said positive sequence tools cannot model large areas of very high penetration renewables. People like the Hawaiians have taken almost an opposite path and added inertia back into their grid to keep the time constants down. To my mind, there has been very little advance in the world of sort of transient grid modeling since, you know, Arrillaga wrote the book on EMTP modeling 25 years ago, 30 years ago. What do you see happening in this area?
Yeah, and I think the industry realizes that these limitations are there for positive sequence. You know, these are the traditional tools that we use in planning. And now you can see the industry and SCE as well transitioning to using more advanced simulation tools like electromagnetic transient to be able to cover some of the things that our positive sequence tools cannot, especially, you know, when you think about those unbalanced conditions or very fast transient type of responses.
Perfect
Yeah,
lead in
we're starting to
to your next panelist.
Yeah. The EMTP programs, though, were written a long time ago. And so I think people like the national labs, and particularly PNNL, are showing some real leadership in trying to solve those systems of equations in parallel to try to get us back to something more like real-time simulation capability. Okay, so that's an awesome presentation. Thank you so much. And a very good lead on to that is now Ang That from NERC. And NERC, of course, have leading this whole area of inverter-based resources, both how to model them, how to analyze what their effects are. We absolutely have systems in the world with very large penetration of renewables like Chile or Australia, where we really don't know what's going on. Ang?
Thanks, Leo. Is my audio coming through okay? All right. Well, my name is Ang That. I'm a senior engineer at NERC. Our team is engineering and security integration. We focus on identifying and IBR-related reliability risks and identifying mitigation measures. I work with Ryan and our team on IBR performance subcommittee, IRPS. That's the new name for the IRPTF that Amir just mentioned. My experience in the power industry covers power system modeling and simulations, EMT studies, hardware the loop testing that Leo just mentioned, the real-time simulation of protection, automation, and control systems, microgrid and energy storage, and then, you know, hands-on developing ultracapacitor energy storage systems, as well as modeling and interconnection of large-scale battery energy storage systems. So I am going to share my screen now. And yeah, I'd like to thank Leo and Charlie for the opportunity today to, you know, for me to join this amazing group of people and attendees have this discussions on this. Every chance we get to outreach to the industry is really important to us to do our job. So, well, before we go in, I'd like to tell this, you know, kind of a story of, you know, the promises that we have with the power electronic enabled future, and the challenges that we are seeing and now and that we foresee is going to come, and then, you know, what we're doing about it. So there's some, you know, some roses, some rain, and then we can have some roses again at the end. So blooming interconnection queue. This is, you know, comparing on the left, you've got two bar charts. You got one 2010 existing capacity. I'm just going to change my pointer mode. And here you have the 2020. So you can see not much has changed within the 10 years. And looking at the Q again, there's 2020-10 Q versus 2021 Q, you see a significant jump, 1 decade later, significant jumps in the IBR resources in the Q. So there's about 1.4 trillion watt. That's about 1 million megawatt in Q. That's greater in, capacity than the 2020 existing capacity. And out of that, 400 gigawatt are batteries. So that's battery alone plus the hybrid batteries, battery hybrids with the solar plants. So that as Amir mentioned, SCE alone, there's going to be 80 gigawatt of battery, right? So, and this is irrefutable evidence, on what the power electronics enabling us, right? We've got climate change, we got social and climate and economic pressures to transition, and that's really driving these changes, and power electronics are at the heart of it. Now, we as the industry very familiar with synchronous machines, or how to protect the system that is mainly driven by the synchronous machine, fault current and things like that. That's the stuff of the past, right? We're really good at that, and all our paradigm is built around that, and we really need to change that thinking around that and say, okay, what do we do differently? Because not only do we need these generations like solar and wind to be clean, we also need batteries to support them. And batteries, I kind of think of it as supporting these renewable plants to interconnect. So they play a really important role in helping with the stability. So how good is the stability if the asset you're going to rely on is not reliable, right? So these are the challenges that we're going to discuss next. So we talked about the promises, really really colorful, a lot of investments in the green tech, and really what those factors are driving a very fast IBR penetration rate, right? As faster than they can be adequately steady for the reliability. So that's one of the major challenges. We have these steady standards in place precisely to be able to assess the reliability impact, and those tools that we use today are hitting the limitations. So we got to look for new tools. As Leo was mentioned earlier, the EMT, electromagnetic transient simulation tool is one of the tools that can provide more visibility and into the assessments of these IBR facilities. And then we have gaps in the interconnection process that has been allowing and letting through some of these studies, these plans, these studies to be completed with the models that are not very high quality. So that requires a significant effort from the industry to drive the change. When it comes to process it, that's has a huge inertia there. And on the other hand, we have different requirements for DERs that are more relevant in the distribution systems, and then for IBRs that are bulk power system connected. So the different requirements and some of the products that are out there, they kind of mature from the distribution side. So some of the settings that we see in kind of that came default, not necessarily good for the IBRs on the transmission system. So we've identified those with the in our disturbance reports and made recommendations accordingly.
We're pushing the end of your session, but please go on, Leo. Recommend you go several minutes into the Q&A.
Okay.
Thank you. Yeah, and then and then another challenge that we have is the lack of specificity in the existing standards requirements, as well as the misapplication of those. So all those spells out the challenges for us, but you know, in the interest of time, I'm going to really quickly go through this. Just taking Odessa 2022 Odessa disturbance report. Just want to highlight, you know, more than a quarter of the trip course was the instantaneous AC overcurrent, and the second was the inverter phase jump, which really is a passive anti-islanding protection that operates on the detective phase jump. Just keep that in mind. You know, in the Q&A session, we can discuss some more. Now, what are we doing about it, right? So first of all, we talked about limitations of the model. So NERC IPS is drafting its for industry common EMT modeling guidelines. We're also trying to stand up a task force, it's pending approval. I invite you guys to join it, learn about EMT modeling. Our goal is to make EMT modeling as approachable as possible. Another angle to this tackling this challenges is enhancing the connection requirements and improvements to FERC, GIAs, and GIPs. NERC has, along with other industries, we have responded to FERC NOPR on these. And also, as in general, the industry adoption of the NERC reliability guidelines. It's really nice to hear, as Amir mentioned, SCE, this has been very helpful for SCE, and they're adopting them. Those are the good examples. And then, we also have work to do at NERC, standard improvements, significant enhancements to our standards to clarify, for more specificity, to be able to address the challenges for the IBRs. And lastly, increase engineering resources to be able to handle this increased, very fast penetration. I'm just quickly gonna skip over this. So this is the IVR strategies at NERC that we have. We analyze the risk. We trying to improve the interconnection process. We're trying to do outreach and share best practices in education, and also working on regulatory enhancements. Just as a PSA, this is another product that we a deliverable that IRPS is working on. It's on the grid forming capability. I mean, how do you define it? How do you spec out functionally, and how do you verify what you're getting is the grid forming, and how do you model them? How to assess the models? So with that, I'd like to conclude my presentation. Leo.
So that's great. One thing you mentioned earlier there, which I'd like to ask you your opinion on. So the largest of the ISO RTOs, PJM, currently has a 3-year wait list for interconnection applications. What do you think about that?
Well, that's, it's demands, right? And like I said, it's one of the challenges that we have is the resourcing, and that we have to improve on that. We have to improve on the engineering resources for sure. That's one of them. Second is the improvement in the interconnection process. You got to keep in mind. We want to do it fast. We also want to do it the right way. We want to do it reliably. So it's a balance that we have to pursue. And FERC, has put out a NOPR to acknowledge that such a delay exists, and they're trying to streamline it. And we have provided comments accordingly. So I think the people want green energy, and we just have to figure out how to do it better and faster.
You brought up verification. Amir brought up sort of the fact that the older tools that have been around a long time, promoted by two of our largest power systems companies, really don't work anymore. And when you look at what caused these outages, almost all of those things turn out to be sort of misinterpretations of the regulations. So Charlie and I can tell you all about that. The phase jump, right? The inverters interpreted a motor spec incorrectly, right? And the fix was simply to put in an average or a delay. So we're not verifying, right? We're putting things in the field, and we don't verify exactly how they're going to work, and then we're sort of surprised by what happens. And it seems like it all comes back to the tools. We don't have the right tools to be able to verify these systems. What do you think?
Absolutely. Some of these functions are not, you cannot represent them in the positive sequence modeling domain. So it limits your ability to assess how those protections are going to act up when there is a grid disturbance. So that's why the tools like EMT, you can better represent these controls and you can assess them. So that's one thing. That's just one part of the equation. The other thing is, okay, you studied it. How do you make sure that you put in what exactly what you study, right? So let's say in the study you don't have phase jump control time, you have it disabled, but when you commission it, it was on, right? So those kind of things are the one that we're trying to address with this EMT modeling guideline that we're working on at IPS, is really matching the model with what's going to be commissioned.
Yeah, and I know that PS CAD group have been very active in your team, right? Andrew Isaacs and
Ong and Leo wanted to interject Roberto, a utility industry technical leader, as a comment that I think might be a really good high-level wrap-up. Is, Ong, how do you balance the need to expedite that amount of queued requests that are all going to require some level of study and engineering evaluation? This balance between rigor that's needed and expediency.
Charlie, that's a $1 billion question right there. And I don't pretend to know the answer, but I can kind of offer what I'm seeing, and kind of everybody can kind of extrapolate on that. The efficiency, we got to increase efficiency. We got to streamline the processes and automate. We got to do a lot of automations of these assessments. And second is the kind of look at the whole paradigm, and really spell out the problem statement. What's really causing these delays? What's really causing these models to not match the product that's in commission, and really solve, get to that root cause and solve it. If we don't, then we just put in band-aids on one after another. So I think those are the key points, right? The efficiency, the streamlining part, using the automation. Second, finding the root problem and fixing it, particularly the processes. And I would say the third is the education and the resource training. We really have to find a way to quickly ramp up, the industry familiarity with the EMT tools. And NERC was working on the EMT SAR standard. We're going to be putting the EMT modeling in a lot of the standards that we have right now. So that would require the majority of the planning engineers to really speed up the EMT experiences. I think that's the part, right? So education, the training, the streamlining, and fixing the processes. And hopefully we can kind of extrapolate from there. Like I said, that's a $1 billion question that the whole industry is trying to solve together.
Well, keep up the great work. You are working in very interesting times.
Thank you, Charlie. It's a very exciting time to be alive.
The Australians put up their hands maybe 6-7 years ago and said, we've got to develop detailed transient models. We've got to move beyond positive sequence, and we've got to, we've also got to put in not just a model of the grid, but we've got to get much better models of the inverters. So I think it's time to move on to the next speaker. I think NERC's role in all of this is critical, and I would add my voice to the suggestion that people get involved. And it's a great working group that you have on.
Thank you, Leo.
So next up is Pat with. I have a lot of inverters in the field still, although people tend to pull inverters out when companies aren't around to service them. But I didn't do a lot of storage work. I did a lot of sort of experimental storage work with people like Jim McDowell, who's also on the call from SAFT, and then Hawk, sort of megawatt system batteries, Santa Rita jail. But Pat has really got tremendous storage experience, and a lot of it to do with vehicles and vehicle networks. But anywhere that ABB has been putting storage, Pat's been there. So Pat, we look forward to your perspective.
Yeah, well, thanks. I'll share the screen here. Yeah, I just listening to the audience or to the other speakers too. I think I have it easier now. Oh, sorry, I haven't shared the right thing here. I have it easier. I'm now a part of ABB's e-mobility group, and we're in the DC fast charger segment. And so now I'm primarily focused on charging batteries, not discharging batteries. But we'll talk about that a little bit and what that means. I'm more in the bus, transit, heavy vehicle charging segment now. But so what does that mean? This is a market that's growing at a rapid pace. ABB's been doing it for 12 years, so we've been a leader in this in the DC fast charging sector. Over 40,000 built globally. So then you think about it, that has to match up to the grid in many different ways all over the globe. So there's a lot of different grid codes and rules out there when you connect to the grid. So I'll start with this slide. If you look at this from a left to right, you'll start seeing why we're going to have challenges or opportunities here moving forward. The vehicle OEMs are building, the light duty, heavy duty, medium duty vehicles, electric vehicles, and we need to charge them. The variables are all moving in the right way to keep having a lot more of these vehicles out into the market. And so that presents you can see there's a huge growth, 2,500 public chargers back in 2012. And now look at today, there's quite a few, and it doesn't look like it's slowing down. But even what I like looking at this picture, it shows the advanced way technology improves with this demand as well. So that the picture on the left is a 50 kilowatt fast charger back in 2012. The picture in the middle is a 360 kilowatt fast charger. Smaller footprint back now. So in just 10 years time. And so that's quite a growth, but it also shows, everyone kind of always looks at batteries and getting energy density down and more energy in a smaller package. It's the same with power electronics. We're doing the exact same thing because you have to. And I think Amir talked a little bit about that as well. So I like showing pictures so you can kind of see these things are coming. This is more public charging space. It looks a lot like fuel stations and things, and they're trying to make it easier for people to use this. But that also shows that they'll start showing up in the grid in many different ways as you look at this. I go into the fleet base, which now you look at it, there are even a lot of different shapes and sizes where you have the outlets sometimes mounted on a pole or a mast arm or a gantry system or up in the roof, or you're on the wall or on a pedestal or on a standalone package. It's trying to match up with those different vehicles that you see there and make sure that they get charged at the right, in the right amount of time so they can get back out into service at the right amount of time. And so it kind of grows into this space where the use cases are being defined, and where then you're starting to see how these chargers are being built and designed to match up to enable that use case. So whether you're doing kind of overnight charging or opportunity charging, corridor charging, things like that to keep the vehicle moving, they're designed for different lengths of charge periods. And you have to kind of see how that works. Whether you're a school bus or a transit bus, it's a different application, probably a different charger. So what does that mean? If you look at the way chargers, when you go back to that 2012 picture, that 50 kilowatt enclosure was a lot bigger than the one that's on this page, and you can see it. But it shows you how the technology has changed too. If you look from the middle of the page, the Terra 184, the 180 kilowatt, and to the left, it's something we call an all-in-one type charger, which means the charger, the device that converts that AC to DC, is in the same enclosure that the dispenser is, the outlet to connect to the vehicle, to that battery. And simple integration on the grid. When you're a grid, you're designing the grid, it's 480 volt coming in, it's three-phase 480 volt coming into that device, and the DC comes out of that dispenser. When you move to the right, it gets a lot more fun because there's you have the charger cabinet that converts that AC to DC, but then someone has to also design the DC cabling and the communications and everything out to the remote outlet. It could be a liquid cooled dispenser, it could be an air cooled dispenser, it could be a pantograph, all different things. And so that gets a lot more project-based feel. You're usually either corridor charging with a high power type thing with its high current, or you're doing more exotic, maybe bus charging or fleet charging in the bottom right. So a lot of different, you can start seeing where they match up. So why do we design these the way we do? If you look at this just shows light duty vehicles. But look at the charge profile of this. The charger always will follow the vehicle's BMS, the charge current enabled, how much charge current that it can handle. So you look at this picture, just for easy reference. If you have a Porsche Taycan that can accept a 250 kilowatt charge, and you plug in close to 20% there, it can handle that all the way up to around 50%. And then it starts slowing it down. Why is it doing that? It's protecting the battery system. These OEMs know how to do that. They've got to make these batteries last a while. And so they're slowing it down. Heat builds up on as you're charging there too. They know how to manage that. So depending on when they plug in on the state of charge, we'll show you the charge rate roughly there. But look at what that just did. If you're designing a site on public charging, you don't know what's plugging in at when, where, why, how, what state of charge they're at, how long they'll be there. There's a lot of different variables to think about and so utilization rate is a tough thing to manage in public charging. So the charger, like all power electronics, we're a current limited device. So that's what you have to think of in mind too, is you're looking at the DC current that it's available to send out. So in this application, it still goes back to volts times amps. It's simple math. So if you have a 200 amp air-cooled dispenser, if you have a 150 kilowatt charger with a 200 amp dispenser and a Ford Mach-E plugs into it that can accept 150 kilowatt, but a Ford Mach-E's only got a 400 volt battery. So it's 400 volts times 200 amps. It's going to be 80 kilowatt. I find a lot of people don't quite follow that math. They go, well, I got a 150 kilowatt charger. It should charge at that. No, it also matters the vehicle's voltage to match up. So if you have a high power charger that can go higher current, 375 amps in that same scenario, you'll have 150 kilowatt output. So it's some things to think about when you're designing. So that pulls from the grid when you on the amount of power required. So
Pat, you're into your individual Q&A, but Leo, recommend Pat wrap up, and then we just jump right into the open Q&A. Or okay. All panelists are fair game.
How about this? I'll just go right to the end slide and we'll just jump into it. Is that all right, Leo? Or
whatever you want. Sure.
Well, just to wrap it up then, when you think about this and how to tie into energy storage and grid integration and things, I started kind of mapping out a few things. So fleet and transit. The nice thing about electrifying fleet and transit, very easy to plan. You know the routes that they're taking, how long they're going to be sitting in their depot, how many stops they're going to do, or what they are. Is it a cement truck? Is it a transit bus? What is it? Is it an Amazon delivery van? Whatever it is, you know it. You can predict it. You can tell it, so you can figure out how to manage it. That's the good thing. The bad thing is, if you're like a transit bus, you might be in a depot application. Amir mentioned that too, or you might be a depot that's been in down urban area that doesn't have any growth area. You can't build more substation or feeder into that plant or that site. So you've got some limitations maybe from the grid or things of how to do that, where maybe energy storage or things can help. Obviously, destination charging is more slow charging. Public charging, you'd see the utilization rates are tough to predict. And you get, we mentioned the weak grids. What if you put these chargers on a weak grid area? Now you've got all those extra voltage and frequency issues where maybe you can have smarter control with charger management systems or automation, maybe microgrid control to manage it, because it is a load that's coming and going. But maybe you have to add other devices on there, like we mentioned. So there's a lot of fun that should be coming in the future here. Maybe I'll stop at that then.
So dating myself now, my former company that made solar inverters made electric drivetrains for Chrysler in the late 90s. And back then there was a real fear that with electric vehicles coming into the grid would not have the capacity to support them. So could you just sort of comment briefly on the growth rate of EVs? And I mean, you mentioned sort of certain feeders might have trouble, but then presumably there's a big movement working on vehicle back to grid and you know, the inverter in the car, possibly, you know, running your house. So give us some sort of futuristic views here.
Okay, well, yeah, so a couple things. So first, you're right, the batteries are increasing. So like for a transit bus, for example, that's more heavy vehicle. The batteries, even when I started in this group 3 years ago, they might have been 100 to 200 kilowatt hours on the bus. They're already about 700 kilowatt hours on a bus. A lot more battery. Now, going back to vehicle, maybe putting this back to the grid, that's probably been looked at more on maybe school bus applications, because that's a nice application. The bus is sitting there. It's got 2 routes in the day. It works in the morning and in the afternoon, and then it sits there for a while. In theory, you've got a lot of time to charge that bus, but then it's also capacity that's there for use. So that's one that's being used at. The part of the thing is then you're connecting to the grid, and some of those maybe those rules of how to do that maybe need to be defined, or maybe to give them a reason why they can use that battery. Because now if you're cycling that vehicle battery, that also can lower life if it's cycled enough. So there's got to start becoming benefits for these folks too, to enable that more.
Yeah, that's great. I think it's really an application like in the late 90s when a lot of us first thought about how batteries and inverters could be used more than just as chargers, you know. Think back. So if you look through the chat, I think one thing that's come out of today that sort of resonated with a lot of people is we possibly keep putting inverter-based resources, particularly renewables, into the grid without a very clear idea of exactly what's going to happen. And we can certainly point to some places in the world like the West Murray Basin where, you know, all the inverters had to be taken out of the field because there were instabilities, there were you know, large dropouts, and so I don't think anybody is advocating for a second that we be deploying things that we haven't studied well. I think that we would all agree that the tools that have been used for the last X years are not really up to the job. Positive sequence tools are not really up to the job. That we need to be embracing better transient tools. And then I think an honest story about the transient tools is they're not very good. They run real slow. They haven't improved in a long time. And so this isn't the reason we have big interconnection queues, but it's certainly a problem, right? We don't have good models. We don't have good programs. The NERC is leading the way. And this is an area that really needs a lot of attention. So I would ask everyone to sort of briefly comment on that. Amir?
Yeah, and you know, honestly, even the EMT tools that are available today, you know, not a lot of, well, I'll speak for SCE in general. We don't have a lot of expertise in using those tools. So we're still in the process of, you know, educating ourselves, looking at some of the recommendations that NERC has provided, adopting some of the, you know, modeling guidelines that have been highlighted by NERC for EMT modeling, to make sure that we get good models through that process. And, you know, also improving our interconnection process so that now in the earlier stages, we're starting to, you know, require EMT models as part of the interconnection process so that we have these models to be able to perform those studies early than, you know, when it's too late. And these things are already on the system and, you know, exhibiting some of these things that we could have prevented by performing those EMT analysis.
So Pat, I'll give you the next crack at that because An gets the final word.
Yeah, see, yes. Maybe what I always thought of is, you know, these different solutions that we talk about with energy storage and solar and microgrids and chargers and things. There's power electronics all over the place there, and they're very fast responding. They are ways to do that, and I think the way controls are being developed to where they all can interact, but maybe a little bit, you know, maybe have more of a single control thoughts. I don't know if that always happens because there's so many different ways of connecting into the grid now. Where it does come more complex, it is tougher to probably model what's actually going on there because there's inputs from all over the place. So it does create a lot more challenges. So I guess that's probably always been the headache a little.
And
Yeah, I think specifically on EMT, just to credit to the positive sequence tool, right? That tool has its use, and we're going to continue to use them, for planning studies, right? But to assess interconnected plants' performance, particularly around right-through performance, whether they can reliably provide grid services, and that will have to rely on the EMT models. And we don't want to just put out recommendations there and kind of leave people hanging. So that's why we trying really hard to stand up the EMT task force. The idea is we're going to have EMT industries experts together. We're going to be compiling resources for people who are starting on this EMT modeling journey. Because if you just got in there, it's overwhelming, and we're thinking through, okay, how can we make this accessible, and and make the learning curve as as easy as possible. So we will be working with the industry to provide these resources to enable that better modeling, better resources. And
so in the world of codes and standards, there's this phrase that says, "Be descriptive, not prescriptive." Right? Tell you what you have to do, but not tell you how to do it. Right? So I was in charge for many years of the so-called islanding or anti-islanding sections of the standard. So that says you have to detect that you're in an island. It doesn't tell you what technique to use. Right? Are we getting to a level of complexity here where the standard should tell you how to do it? Charlie, what's your opinion?
I remain old school. Standards should be non-prescriptive. Give you the performance requirement, leave it to industry to implement. For a comprehensive total operational success, I don't know if we could leave it that loose anymore. Leo, I do want to jump in as we head into the end and ask Pat one final question. In my experience, innovation doesn't happen until someone figures out how to make money innovating. I didn't see V2G unless I missed it. Does ABB see a commercial pathway to V2G? Is it in your product roadmap?
Yeah, yes, it is in our product roadmap. We're doing pilot projects over in Europe right now. I kind of mentioned a little bit with, school bus application seems to be the easiest low-hanging fruit with it, just because of the way the vehicle is sitting there. And it is a little bit bigger battery, so you have the chance, and with the whole fleet, you'd have a chance to engage it. But I also think the rules have to start showing value for that, or giving the operator of that bus value to use their battery to help the grid. I mean, if all you're doing is degrading your vehicle battery life and you're not getting benefits, it doesn't help.
So Leo, back to your question, maybe it's application specific. We start giving more firm guidance of how you meet requirements from an implementation. I think V2G could be a context where the standards explore that. Well, thank you, Leo, our moderator. Thank you, panelists, Pat, Ang, Amir. Thank you to Carly, Courtney, and Shannon, the organizers of this webinar series, and the people who made today happen. Thank you very much. Want to highlight upcoming webinars in the GSL sponsored series, Long Duration Storage Policy and Economics, led by Jeremy, and then a really exciting new area of DOE-backed activity, Energy Storage for Social Equity, moderated by Jennifer Yoshimura, our program lead here at PNNL. And I do want a final statement on Grid Storage Launchpad. That will be a new facility, DOE and State of Washington funding at PNNL, that's going to collaborate with industry to validate the performance of emerging grid storage technologies, mainly batteries, aimed at meeting storage shot targets like 5 cents per levelized cost. We'll be in business 2024, looking to collaborate with industry to validate performance to ultimately accelerate the adoption of the next generation of energy storage technologies. Shannon, I'll hand it to you. I believe we may be ready to close out the session.
Yes, thank you, Charlie. Great job, everybody.
And thank you to the audience.